Levitating in solitude. The heart word would have the ingrained dream map to reach the divine shape of a solemn God who is guiding the sap. One day you will go deep and dark to find your roots where tomorrow was conceived. And in the ruins you will find the warmth of your peers still walking on the God particles. Religion now takes over the mob, ready to plunge into yellow sands of dry river. The hopes and promises give you a horizon far away. You want to touch this furnace that bring the burning day of solitude. All right.
Wow.
Ignore that random voice in the background was not mine. Neither was that laugh. So this poem called "Levitating in Solitude," wait, is was written by Satish Verma. I have no idea who that is, and frankly, it seems to have very little to do with physics, but it sounded beautiful, and I found it. So there you go. Now, what is relevant is the levitation part because today we are.
But what is this? What are we watching?
Yeah. That was really bad. What is this? SG2 on Space, the only weekly space show. Okay, you can go there, youtube.com/@shinga/streams. Another way you can actually find us now, although I have not quite figured out how to do this live, is you could also find us on Spotify. So this is a new development. So you can go to you can go to this link. So podcasters.spotify.com/pod/show/SG2 on space. Like I said, those episodes are not going to be live and they are going to be purely audio. So if you're listening to that on that right now, you know what I'm talking about. If you're not, if you're watching a YouTube video, then point is you can go there and hear all the episodes. So just will not be live. All right. So with that, this disembodied voice in the background, you probably need to know who that is. I've been babbling on and on. There. Got it. Dr. Leonard Kramer, how's it going?
I'm here. I'm very good. Better than
better than you deserve, right?
Right. How are you? How are you, Shen?
Well,
Yeah.
I
What?
thought I took an hour and a half nap, and then I had to walk my dog. So I guess I feel better than before that. I don't know.
Oh.
So
Did you take a day off from? Did you not work today? You took a day off, or?
No, I did. I did work today. I need to do more work later because clearly I was not expecting my nap to be so long. I had some car issues I need to get resolved. So
Yeah.
so I was working remote today.
Oh, okay.
But yeah. Anyways, point is, good to see you with your hand gestures. With your head. Okay. Well, I mean, why not? Way to be expressive, right? So, as long as it's not blocking my head. This is episode 175, and like I just said, doing this for a few years. But we actually never covered anything related to the topic you brought up. Maybe it's because I know very little about it. I just hear that that it's one of the most exciting things in physics, and also it has a lot of practical applications, namely superconductivity. In a tangential way, I suppose is related to the levitation. So that's why that poem was chosen. But you're kind of an expert in some respects, giving me a weird look, but more knowledgeable than I am. So what is superconductivity? Let's just
So, what is superconductivity? So let's see, where do I begin with this? At the beginning of the 20th century, people were starting to understand about classical physics and electromagnetism and electricity and stuff like that. And around 1910 or so, they had developed the technology for producing liquid helium. And that's a cryogenic liquid, and so a lot of people were doing stuff with it, and there was interest in the resistivity. Resistivity is how much electrical device will will resist current, electric current. So if you put a voltage across a resistor, then a certain amount of current will flow through it, and heat will emanate and all that stuff. And so classically, it's thought that what's happening is the electrons are moving through the conductor, and they're essentially colliding with the ions. Now, at that point, in the early 20th century, we didn't really have a complete picture of all of that, but people were interested in things like conductivity, and there were some practical aspects of it. So there was a guy named, I think his name, let me see, I had him up here, a guy named Otto. The history of um, and I think he was Austrian. So he was
Auto what?
no, his last name was Otto. I'm looking for it here.
Oh, okay.
Embarrassing. I just had it up because I actually had heard of him, and then I forgot. And uh,
Well, I mean, I was going to say the resistivity, the classical one, is this like an example of some of the things? Maybe.
yeah. Oh, yeah, that's good. So what he was doing was he had this liquid helium. Liquid helium is very, very cold cryogenic material, and so it had long been observed that as you reduce the temperature of a resistor, that its conductivity goes up, its resistivity declines, and that can be understood as if, well, the ions are bouncing around a lot, and so if the ions are almost stationary or moving slowly, then there's a clean path for all the electrons to move through to provide the conduction, and or to provide the current. But what was observed was this remarkable thing, that as the temperature of the substance, and he was using mercury at the time. Mercury is a very good conductor, and of course, when it's at cryogenic temperature, it's a hard metal, right? But he was subjecting it to liquid helium and getting it down to about 4 Kelvin, which is just a few degrees above absolute zero. And he observed that the resistivity, at a particular what's called critical temperature, the resistivity went down to zero. And we're not talking about like maybe just near zero. It was zero. And subsequently, people have examined all different kinds of materials, and they observed this phenomenon. And it's almost, there he is. Honest, yeah.
Sure, this is a guy, right? So
yeah. And it looks like a friendly kind of gentleman. You might want to.
I mean,
yeah. So
he's not wearing a headband though.
He got that's true, but I have some for him. But he got the Nobel Prize for this in 1913.
Okay.
For this very weird kind of observation, that the resistivity goes down to zero. And it's almost like, what it means is that you can have this material, and as long as you keep it cold, it'll continue to be a perfect conductor. Doesn't have any. And so if you induce a current flowing in it, like if you have a ring of this material, or even if you just have a disc or just a material, and you induce a current to be flowing in it, it magnetizes, and that current will flow forever. It doesn't ever stop. So this is a very, very strange phenomenon. A few physicists at the end of the 19th century were thinking that at absolute zero, if you got it all the way down to zero, that the resistivity would go up, because they thought, well, maybe the electrons become frozen or something like that. But that's not what's observed at all. So this was a thing, an observation, and people struggled with it for something like 30 years, until the 1950s. I think some other theories started to appear about what was going on. And of course, it has to do with quantum mechanics. So there's two kinds of superconductors. One of them's called type 1 or type 1 and type 2.
Type 1 and type 2, right?
Type 2. That he was looking at the type 1 superconductors, and they have certain kinds of properties. They will exclude a magnetic field, because if you try to move them, for example, whenever you have a magnet and a conductor, the magnet will produce a current, and the current will be induced in such a way that it will resist the magnetic field. So effectively, it will these kind of superconductors will expel, and they sort of expel the magnetic field, and they basically reflect any kind of magnetic force that's applied to them. And so it's very common to see these levitating. You can levitate a magnet, some of these strong magnets. One problem there's there's like practical applications, because if we had wires that had zero conductivity, we could generate electricity like very far away, maybe with solar cells or something in the desert, and then we could transmit it without any cost, without any losses, to the whole rest of the continent. But there's practical limitations having to do with the fact that this only works at very, very cold temperatures. And the reason it works so that gets into the physics of what's going on with superconductors, and it's the quantum mechanics is very interesting.
Let me ask,
yeah.
In our daily life, have we seen this somewhere? Is it
well, I know that there are groups of people who are working on using superconductors for magnetic shielding. That's a thing. In other words, certain kinds of instrumentation that needs to be shielded from the ambient magnetic field. They'll make a kind of envelope, like a metal. I actually think it's made out of lead, foil. I don't know why they use lead, but I could be wrong about that too. And then at cryogenic temperature, you can put your device inside this envelope and close it, and then immerse it in a liquid helium.
Okay.
And yeah, that kind of thing. So you can demagnetize things or shield things from magnetic fields. Obviously, there's proposals to use it for levitation, using frictionless, frictionless transportation. And there's been a long-term quest to improve, to get superconductors that are superconducting at higher and higher temperatures. And it wasn't until fairly recently, I don't know the exact date, but something like 40 years ago, there was a kind of ceramic material that has yttrium, barium, and something else in it,
what
oxygen.
These are, you said
yttrium. Okay. Yeah, yttrium. It's a metal. It's one of the metals that's over on the left side of the periodic table.
I was trying to actually. You sent me this really interesting video, I think yesterday. So I was trying to see if I could.
Okay, everyone. Today I'm going to be showing you the quantum locking experiment.
Oh, this guy's good, but we haven't talked about it. I like this guy. He explains things well.
Let me know if you can actually hear the audio.
I heard it.
Now, this is one of the coolest experiments, in my opinion, that I've ever done on my channel.
You can.
So first, I'm going to show the quantum locking in action, and it's really amazing. And then after down, we need some liquid nitrogen.
This is exactly what I need: liquid nitrogen.
We need.
Now I'm just going to drop my superconducting puck in here.
I feel like I'm getting some of these material myself to do this.
Yeah, so I'm going to try a few things here. First, I'll try putting a small magnet on the superconductor and show you what happens. And then I'll be putting the superconductor on some bigger magnets. And then finally, I'll be putting it on a track where you can push it around. And it's really amazing what happens.
Here, check it out.
Watch me place the magnet on the superconductor.
It levitates. See?
Watch this.
You can move the whole thing. Okay. In order not to watch the whole thing,
it always comes back to the same spot.
So this is a type 2.
Get it even closer.
Superconductor.
The one.
Notice how it's not touching, but I can push the superconductor. So now I'm going to place it on this track that just has rows of neodymium magnets, so that these are opposite poles. So what it does is it creates a symmetric magnetic field in this direction, but not in this direction. Now watch what we can do. Okay, now watch this.
See?
Yeah.
Beautiful.
You see, it obviously has some kind of applications that you could use for levitation. And what I was saying was that this is the ceramic material that is a superconductor at a higher temperature. Liquid nitrogen's easy, is much higher temperature. See, he's touching it with his finger. I mean, it's cold, but so yeah.
It gets like way more, like you could do it on the bottom as well.
On the bottom, yeah. So this is that
Um,
locking phenomenon, and that only affects that's only with type 2 superconductors.
So this the one that the guy found earlier back in the early 20th century, that was type 1.
That was a type 1, and there's a different kind of physics that's associated with that, or slightly different physics. We'll talk about that if you want. Oh, see, you can
You can
yeah,
levitate
you can
bread.
levitate, rotate your sandwich.
I mean, sure, it sounds completely pointless here, but think about the practical applications if you could adapt it.
Right. So
So
people have thought about levitating trains, using it as a frictionless
well,
kind of.
we do have magnetically levitated trains. There's a few of them in the world.
I think in Germany especially has been a lot of research in that area.
But they also helped in Shanghai in China. There's I think.
Oh yeah, yeah. I
well.
think I've read about that also.
Yep. So, I mean, from the very obvious example, yes. This guy could explain everything, but I don't want him to. Let's have Leonard do it. No, Leonard.
Okay. Well, there's the diagram there. That's what I was describing, where he has the resistivity and the temperature, and if you get it down below a certain temperature, then it suddenly becomes 0. Not like some fraction of an ohm, but I mean 0, and the physics has to do with the lattice, what they call lattice. Lattice means that all of the ions are arranged in a kind of crystal form, and they're sort of fixed relative to each other.
Right.
And so what I've seen this analogy of, like, if you had a room and it was all filled with these punching bags, right? Well, you could run right through that room because there's a lot of room between the punching bags. But if the punching bags are all moving around because they're at a higher temperature, then you would have much more difficulty. You'd end up bouncing and hitting the punching bags. It would slow you down. So that's the analogy. And as the temperature gets lower and lower, then the bouncing of the punching bags decreases, right? But at a certain point, if the temperature is very low, you do reduce your resistivity, but there's a limit to that. That physics is limited. And so what happens is that it's the nature of the electrons that they are what are called, we talked about this a little bit before, but they're called fermions, which means they have a spin of a 1/2 integer spin. And that's associated with the fact that the electrons can't get into the same state. Right. So that's some people know about the Pauli exclusion principle. Yeah. And then the various the shell structure of atoms, like when atoms have electron clouds around them, they form some structured arrangements, and you can only have 2 electrons because they're in opposite spins. And there's a certain affinity that the electrons have for each other because they have opposite spin. Well, in this lattice structure, so ordinarily the solid material, if it's a conductor, the electrons are just sort of swimming around, almost like a gas, in the way that I just described it, and they're bouncing into the ions. The electrons are something like almost 20,000 times smaller in mass, and so they end up going much faster than the ions. The ions don't move at all because they're fixed in a rigid lattice for these kinds of materials. But what happens is that the electron, and maybe one of the videos has a diagram, but the electron, if it's all by itself in this lattice, it has a tendency to pull the ions closer to it, but they're not completely free to move. So it's like the lattice gets a distortion in it, like it gets all pulled together. And so it has this tendency to zero out the charge, the negative electric charge of the ion relative to another electron that might be nearby. So the electrons, ordinarily two electrons that have opposite spin, for example, will repel each other. But if you cool things down so that the lattice is very rigid, and also, yeah, hey, there's the punching bags. But anyway,
that was I'm trying to follow along with.
Yeah, that's a model. So there it is. Yeah.
Yeah,
So if you pull them together, it pulls them together, and so there's a shielding effect. So imagine there's two electrons, right? So they will repel each other. But if in a kind of lattice of ions, the ions get pulled in, and they have this tendency to shield the electron, or neutralize its charge relative to the other electron, and that other electron is doing the same thing. So effectively, the electrons don't see each other's charge, so they don't repel, and there's a very weak affinity that the two electrons have for each other, because as an attribute of their opposite spin. And so they add together, the spins add together to make something called a boson. So they're not bosons, there's two fermions, but they act like a boson, and that kind of boson can move through the lattice without any interference. So it's not it and they can all get into the same state, and they can all move together. And that's the explanation for the superconductivity. This was discovered by a group of three scientists in the late 50s, and I only remember the name of one of them. His name was Cooper.
Is this one BCS theory? Like
the BCS theory, yeah. The BCS theory.
I think for Cooper, right?
And
John Bardeen.
Bardeen.
Oh, there we go.
Yeah.
Leon Cooper and John Schrieffer.
So this is called, and there it is, 1957. So they developed this theory that I'm talking about, where the lattice will shield the electron's electrical charge, but then there's a remaining attraction that the two electrons have for each other by virtue of their spin, and so they combine together as a pair, and they call it a Cooper pair. And the Cooper pair can actually be pretty long compared to the lattice. Like it could be, really, the two electrons could be very far apart, and still, or in the conduction band, and they will still behave. They will behave very similar to each other, and as long as the temperature's cold and there's no disturbances, then they will stick together like a kind of weird kind of electron atom.
Okay, so, like in this diagram here, the red ones are what, and the blue ones?
The red ones are the ions, and they're fixed together in that fence matrix. Yeah, so that's what happens.
So he's using this like, oh look, these. Okay. Yeah. Okay.
Yeah, and then there should be another electron far away, and it doesn't see that electron. It doesn't see the other one's electric charge because it's shielded. But it does see it does. There is a remaining very weak attractive force between them, and actually they're attracted to the distortion of each of the electrons, and so they pair together, and they have a net spin of 0, which turns them into a boson, or they behave like a boson. So all of the Cooper pairs in this, and there's not just one. There's like there's as many as there are ions, in the material, and so they all behave the same. And so that's the classical explanation. And I think the BCS group, they had papers written about this with long calculations involving quantum mechanics and wave functions and spin and degrees of freedom and that sort of thing.
Basically, if you want to dive into the physics, you definitely can.
Yeah,
Right.
but this I think this is enough. I think this is enough. You know, I did study it in graduate school, so you know we had a little unit on superconductivity and what was going on here. But it's not, you know, obviously it's not my field. But
And there are places, here you go, for anyone who's
yeah,
interested. This is a 1957 paper, which Leonard was just talking about, which you could read on if you want to read all the quantum physics that explains that nice graphic. This is probably going to ask me to pay for it. But
yeah.
microscopic theory of superconductivity. So with that. All
And
right.
that's all I had to say.
That's all?
Well, actually, we can talk about locking. So that phenomenon that I don't know that the YouTube video that you show, the guy that I said I really like the way he explains things.
Right.
I like his enthusiasm. He's all bubbly and excited about it. So what happens is that for the type 2, there can be impurities, and so it's not a perfect superconductor. There are little points, or and really there's like billions of points that are not superconducting, and so the magnetic field can penetrate through, and so it will curve, you know, through it. So if there's an inhomogeneous, meaning a magnetic field that's not uniform throughout, then the field will kind of get, it acts like a rigid sort of supporting structure. And so that's why when you take the magnet and you move it close to the chilled cold superconductor, it will kind of stick there, because some of the magnetic field is piercing the superconductor, and the rest of the part of the superconductor that's really superconducting doesn't have any field going through it, but there's little remnants of it that will penetrate, and so that's a characteristic that allows you to hold it closely, and so that's called locking. And there you can see things like eddy currents that it talks about. Some people probably know that, you know, if you have even at room temperature, doesn't have anything to do really with superconductivity, but if you have two magnets that are very close to each other, and you try to move a piece of non-magnetic metal, or any kind of conducting material like copper or aluminum through it, it'll resist. You know, it will try to damp your motion through it. Sometimes these are used as dampers to dampen motion, and that's because when the electrons in a conductor are moving through a magnetic field, it induces some contrary currents that are in the metal that resist, that are opposite to the um, to the imposed magnet. In other words, if you have this imposed magnet, I think that's kind of what that's explaining there to some extent. I'm not sure exactly what that picture is about.
Well, it's saying
But
inside a material subjected to a changing external magnetic field, small electric currents known as eddy currents.
Eddy currents, right?
Normally, these eddy currents decay away rapidly, but if the material is superconducting, there is no resistance, and they will not only be able to, but will be required to persist indefinitely.
That's right. And so the effect for the superconductor is that it will just resist the motion of the magnet, and that's where you get the levitation phenomenon. So now for a type A, the kind of a superconductor that was originally discovered, you know, in the early 20th century, for a type A type of material, that's not the case. In other words, you wouldn't be able to, it wouldn't stick. It would just like, it would still repel, but it would kind of like fall off. You know, you wouldn't be able to hold it in one position.
This is what he means by impurities, right?
Yeah. So
the uniform perfectly. Let's imagine we have one with impurities inside of it.
So this is for the type 2 type of
Type
superconductor.
2 exposed to a strong.
Am I right? Did I say that right, or did I get confused about type 2? Right?
No, you did.
Yeah.
Type 2 superconductor. Yeah.
So the type 2 has like these rubber bands that stick through it, and the current will flow around those, but
this effect by the way, is called it's named after somebody.
Oh,
Meissner effect.
a Meissner effect.
Yeah, where
Yeah.
the magnetic field, I guess, just goes around.
Yeah, it will expel the magnetic field. And I don't know what that is.
Image taken with the scanning squid microscopy of the yttrium, barium, copper oxide film subjected to liquid helium temperature, 4 degrees Kelvin.
Yeah, okay.
Black spots are vortices created by the eddy currents around the impurities, while the blue and white regions are where all the magnetic flux have been expelled.
Oh, okay.
Wow.
That's cool.
You can actually
must be exploiting a Zeeman effect or some kind of quantum mechanical effect. I'm not exactly sure how that was imaged, but that's kind of cool. So that's the idea anyway. That YB is it YB yttrium,
yttrium, barium,
barium, and
this one
copper.
also copper.
Yttrium, barium, copper. Okay, so that's the common one, and they're not expensive. There's a guy on YouTube who actually manufactured this. It is pretty heavy duty chemistry or chemical engineering to do it. You need a furnace and a vacuum thing, but it's not. There's nothing like dangerous about it.
So basically, anybody could go and buy these materials and go build yourself a superconductor.
Yeah, with sufficient practice, I presume.
So, well, like the guy on the YouTube video, which built all those tracks and just demonstrated what you could do. You could do that yourself, right?
Yeah. You can buy this ceramic material. I don't think it's extremely expensive. You do need some liquid nitrogen.
Where do you get that?
I think it's commonly available, but I've never. I did do a quick look on Amazon for liquid nitrogen. It just seemed kind of too expensive. But I think that there's less expensive ways if you're a laboratory, because it's a very common refrigerant, material for all kinds of things that people use liquid nitrogen for.
So basically, in terms of that particular ceramic material, that one it's pretty you can just find it online and purchase it. It's not expensive.
I think so.
Right.
And so there's a search now. People have been working on trying to find materials or a theoretical way of explaining or producing or predicting a material that could do this at room temperature. And so there is some talk about a material. A few years ago, some group did say that they had something that would work at room temperature, but the catch is that they needed to compress it to a pressure that was equivalent to the center of the Earth. Well, so it was two, but they did say that it became superconducting at room temperature. Lately, I mean, within the past few months or so, I think I saw a report that they think maybe it was not reproducible, and I think a group in China, said they weren't able to reproduce that result. So
if we could get room temperature ones, what would that mean?
Well, if we had room temperature superconductors, I mean, we can do what I mentioned at the beginning of this session here. Was we could have power transmission from great distances without any loss. If we had that. Now I have to say, it's not you can't impose a infinite current on it. If you try to drive too much current, then it will break down. And there is a limit to how much current. And I don't know the practical aspects of that. I don't think people have really paid very much attention to the practical aspiration of having a superconducting material for engineering uses, because we haven't been able to achieve that yet. So, other than for these specialized applications. Now those
what we have to talk about. Okay, let's
is it time?
Go ahead. Maybe. I mean, I don't know. Who's to say?
What would you like? What's it time to talk about now?
Did we talked about Bigfoot some time ago, right? But let's talk about this video well,
Okay.
actually, you know what? You need to finish your thought. I hate interrupting you in the middle.
No, that's okay. That's kind of all I wanted to say about it. I mean, I think that's enough. We type 1, type 2 superconductors, and it was discovered when liquid helium came online in the early part of the 20th century. You know.
Well, I mean, yeah, like being able to explain the quantum phenomenon as well, how the electrons are able to behave, as well as the quantum locking effect. So, all right, I mean, you can obviously dive into way more complicated physics, but for now, you know, let's talk about one of my favorite topics, which is what could it possibly be? All right, I don't know. Here, tell me what you think of this, and you can do the normal thing you do, where this is supposedly a large UFO flying over the moon.
Looks like my cappuccino. So
Does that mean? I mean, no? Yeah. So
I think it's a close up of my morning coffee. And
this was flying across the moon supposedly on September 29th, 2022. And according to the person who put it up, it was taken in China with a long-range professional camera. And this is the Mexican journalist and UFO researcher Jamie Maussan. I obtained it and deemed it credible. He says it's one of the most interesting UFO videos in recent years. So what do you think?
I don't know. That looks pretty compelling. What do you want me to say? It looks like some kind of alien spacecraft of some sort.
Okay.
Or it doesn't look like what I would expect I wouldn't expect a disc. I wouldn't expect a disc with a hole in the bottom of it like that. So I don't know. And the thing is, you know, like if this is in the vicinity of the moon, this is a huge object. This object is hundreds of kilometers.
Well,
but
yeah.
if it's in orbit around the Earth, then, you know, I don't know. Then there's always the case that it's a Photoshop fake. But I
don't know.
Yeah.
And that's a problem these days. So anything that looks bad, you could just say,
yeah.
You could say, oh, you know, that does not look realistic.
I know.
If something looks good, though, you could say it's Photoshop. So how would you?
You can't. We're preempted by our anti-alien bias, because the first thing that we have to cope with is the fact that everybody has a camera. There's like an order of magnitude more cameras on the Earth than there are people, right? And so you would expect that if the aliens were here, that we'd have lots and lots of really good photographs of it. And so what we end up with is, you know, like very blurry. You've heard me make the joke about the blur, their blur cloaking device, blurred image cloaking device. And so, but you know.
And enough of that. I don't know who that guy is.
I don't know. He looks like a host of a UFO show or something. I don't know.
He might be. All right. So I think that's enough for now. But Leonard remains unconvinced, which is fine.
Well, are you convinced?
No, I need more info. You can't just show me a random video and expect me to
That's
be,
right. Yeah,
like,
we need clear evidence, you know. And now we can talk about that sometime, about, like, Carl Sagan said, you know, extraordinary claims require extraordinary evidence, right?
Yes, he did say that. However,
I seem to have a delay. That's kind of interesting, isn't it? The video slows down on me from time to time.
Is your brain's working too fast?
Yeah. I get that a lot.
Wow. Okay. I gave you a compliment, and then you went ahead and just ran with it. I see. All right. Okay. Well, all jokes aside, we are at the conclusion of our show. This has
Aw.
been SG2 on Space. I'm not going to bother playing on Beyond Video. Anyways. I don't know why you were just pointing at me, but I forgot to say in the beginning, thank you to our supporters and Patreons, Kyle Baker, Sam Welsh, for their financial support every month, and as well as I'm going to support I guess
acknowledge
Atum Ra, who helped produce the show for over a year before we decided to go ahead and just do it with our own efforts here. With that said, remember that you can support the show on patreon.com/SG2OnSpace. Do not support the show on Facebook or anything like that. It's still down, unfortunately. Do check out the audio episodes on podcasters.spotify.com/pod/show/SG2OnSpace. However, if that is way too much for you to remember, it's easy. Just if you have Spotify, just look up SG2 on Space, and that will be the only one that's there. So, and this episode will be placed there, the audio version of it, soon. All right, and with that, we will be back next week. What day? What day?
Tuesday. Should be Tuesday.
Tuesday. So if you're watching this live, you may have realized it's actually not Tuesday. It's Thursday, but that's
just
exceptional. It'll be Tuesday next week, 6:30 p.m. U.S. Central. All right.
I look forward to it. I live for that.
All right, Leonard lives for that, so that's something, right? Look up, because you never know what you will see. All right, see you all next week.
Namaste. Mwah!